So what we're going to cover today is to look at how do surgeons derive the IOL power, how is it being calculated. Of course, before the calculation can be done, there needs to be some key measurements performed on the patient before selecting the IOL power. And we're also going to discuss about various methods of biometry and keratometry. And finally, we're going to summarize how A constants or lens constants are personalized. And at the end of the session, I've got a little activity that I've planned for. And we look at the timing, and we may be able to do that activity after this patient satisfaction, which is an accurate IOL power that has been implanted into the patient's eye. First of all, we need to look at accurate measurements. So measurements of the patient's eye is really fundamental to getting the accurate power. The correct calculations, meaning the correct formulas or appropriate formulas are being used. And this is something that the surgeon needs to address with the patient in terms of managing the patient's expectations. So let's first of all look at some of the key measurements that are required. So when I say key measurements, these are the common measurements that most formulas would require, but there are some formulas that require even more measurements. But let's look at the common ones. So let's look at keratometry and corneal topography. So keratometry or corneal topography is required because the formulas need to know what is the corneal refractive power. So only when the corneal refractive power is being determined, then the formulas can work to calculate what is the IOL power that needs to go with this corneal refractive power. So the power of the cornea is it's performed right by keratometry or corneal topography. So as we had mentioned earlier on last week when we discussed about diagnostic instruments, keratometry and corneal topography both measure corneal power, but they do it in quite a different way. So keratometry instrument does have a better measurement of the true central corneal power. However, corneal topography, it's not measuring the exact central power, but it is a simulated central power, right, which is derived from the peripheral parts of the cornea and then extrapolated to the center. So it is kind of, it's what they call a simulated cornea central power. Keratometry and topography both would give the degree and direction, meaning the axis or meridian of astigmatism. And they would show both the steep and flat meridian. So the meridian with higher power or the meridian with low power, they are being represented. So how are they represented? They're represented in axis, of course in power, but they also need to determine where is the location of that corneal power. So it's indicated by means of axis from 0 to 180, right, in a counterclockwise direction, right? So going from right to left, right? So whether it's the left eye or right eye, it's always going in a counterclockwise direction. Okay, so preoperative measurements of keratometry and topography, different kinds of keratometry in fact, do not always correlate, okay, because different brands keratometry have a different area of measurement, yeah, so, and also topography, it's not measuring the central power, as I mentioned, it's measuring the peripheral power, and then extrapolating that information to the center. Right, so usually manual keratometry measures 3.2 millimeters apart of the central cornea. So the area of measurement is 3.2 millimeters of the central cornea. Automated keratometry does a little bit smaller area. So for example, the IOL master or even the auto refractors, they usually measure 2.5 millimeters, right? And the Lenstar does even lower, but it has two areas of measurement, 2.2 millimeters and 1.7 millimeters. But corneal topography are different. As I said, it measures thousands of points between 3 millimeter to the 4.5 millimeter zone. So typically within the 3 millimeter zone, the central area, there's no data points. So whatever data points is collected from 3 to 4.5 millimeter, that is being extrapolated to the center, and then that predicts what is the central corneal power. So for that reason, most surgeons actually prefer to use keratometry readings for calculation rather than corneal topography readings. So there can be some errors in cornea measurements that can lead to IOL power calculation errors, right? So there can be some errors that's caused by cornea scars, which cause irregular astigmatism. So although these would give a reading on the keratometry readings, they are not a good representation of the average cornea power. Prior corneal refractive surgery also does not give you accurate cornea power readings. Reason is because keratometry works with a certain relationship in terms of the curvature of the anterior and posterior cornea. And with corneal refractive surgery, that relationship between the anterior and posterior cornea is changed. So whatever readings that's coming out from keratometry instruments for these prior corneal refractive surgery eyes, they are not going to be accurate. Corneal transplantation again presents a different set of challenge. This would probably have some degree of irregular astigmatism. Dry eyes during keratometry is also a key problem to keratometry errors, right? So one of the points to take note of, if there is dry eyes issue during keratometry, you need to be putting in some lubricating eye drops, or you need to treat the dry eye issue before performing keratometry measurements. One of the indications of looking at these errors in cornea power measurements, when you look at the keratometry readings and you see a certain significant amount of inconsistency in terms of the readings. So if you're taking a few readings from the same instrument, they should be quite close. If they are not similar enough, then there could be a problem in terms of these that have just been mentioned. Contact lens wear prior to measurement is also going to cause problems because this can alter the shape of the cornea and measure an incorrect corneal power. Right, so it depends on the type of contact lens that's being worn. Soft contact lenses or hard contact lenses both needs to be abstained before measurements. So the period of abstainment depends on the type of contact lens. For hard contact lenses, you need much more longer period of time before you can perform the measurements. So some sources have quoted between 3 weeks to 4 weeks for hard contact lenses, soft contact lenses 2 weeks. For and inaccurate measurements can also happen. This can happen with result of the improper positioning of patients' head on the instrument. So as we perform the keratometry measurements, the patient needs to fixate their chin and their forehead against the instrument. If that fixation does not occur properly, then inaccurate measurement can happen because you may be measuring at an angle which is not correlating to the visual axis. An incorrect conversion to diopters. So this one is a little bit rare to happen. Most keratometers do the automatic conversion. So unless you are performing the conversion manually, most keratometers do this automatically. So when I talk about keratometry readings, I just want to show you some examples. So here you can see keratometry readings that are performed by manual process. So manual keratometry giving you these readings. So you can see K1 is 44, K2 is 45.62. The average K is 44.81. So this is for the right eye. But when you look at the IOL master K readings for the very same patient and the same eye, you can see that there's some difference in the readings comparing it to the manual keratometry. So these are IOL master keratometry. It's different from manual keratometry. So just and if you look further down the page, you've got this autorefractor keratometry. Again, that's different from what is seen in the previous two instruments, right? So for different instruments, you can get different readings for the same patient and the same eye, right? So this is because of many variables. One is because of the different instruments that measure different cornea surface areas. Secondly, is also it could be measurement error due to the technician performing it. Third, it could be due to dry eye, right? So it could be by the time the patient reaches a different instrument, the eyes are not as optimum as before, and you can have this differences in the readings. So the key here is to try to get these readings as close together as possible. And the surgeon will probably have one keratometer that he would trust the most. The surgeon would most rely on, and the other keratometers are probably just there for him to make a cross-reference check. So the key is which instrument is the surgeon most comfortable with using, and which one has he been consistently using for his IOL calculations. So that would be the one that is likely going to be best used for the surgeon. So just going to check if there's any questions. Okay, no questions. So feel free to type in any questions along the way. I'll check them as I go along. Okay, biometry, right? So we've talked about keratometry, which measures corneal power. So the other measurement that is key to IOL calculations is biometry. So biometry is the measurement of ocular distances. So a lot of us think that biometry is just axial length measurement, which is not true. So biometry is any ocular distances that are measured within the patient's eye. So axial length is one of them. Anterior chamber depth is also another, which is commonly used. Sometimes the biometers also measure the lens thickness, so the crystalline lens thickness, which is also used for calculations in some formulas, right? And so there are a few different types of biometry that are currently being used in the market. So ultrasound biometry, it's still used, but it's getting less popular nowadays as compared to optical coherence biometry, which is well known with the brands of IOL Master and the Lenstar instruments. Ultrasound biometry uses a reflection of sound waves, so it is an ultrasound instrument that emits ultrasound waves, and that wave is reflected off the back of the eye where the macula is, and then that reflection is then measured by the instrument and calculated accordingly to find out what is the axial length of the patient's eye. So one of the disadvantages with using ultrasound methods, especially for contact applanation, is that there is compression of the cornea, and that results in an inaccurate measurement of the axial length. There is another version of the ultrasound of using ultrasound biometry, which is using an immersion method. So basically what they do is they do not have a direct contact of the ultrasound probe against the patient's eye, but rather immerse it in some fluid such as saline. So you need some kind of cup that is held over the patient's cornea and immersing that ultrasound probe in that device filled with saline, right? So it does not touch the cornea, so there is no there is no error due to compression of the cornea. But if you compare ultrasound biometry to optical biometry, there's always the chance that in immersion biometry, you're not measuring the true visual axis because the probe being held so close to the patient's eye, it is quite impossible for the patient to fixate at the ultrasound probe, right? So in terms of fixation, it is not possible, and therefore you may not be measuring the true visual axis, but rather you may be measuring the anatomical axis, which sometimes does not correlate very well to the visual axis. Now the other form of biometry, it's right now known as the gold standard. It is optical coherence biometry, which uses reflection of infrared light from the back of the eye, and that reflection of light it's known to be directly over the patient's macula or fovea, because in such instruments you allow the patient to fixate into the instrument. Let me see if I have the instrument here. I'm not sure if have you seen a IOL Master instrument before. So it is let me just open it up. So just for the benefit of those that did not attend the diagnostic session, I'm going to show you what the different parameters look like. Alright, so I don't have a picture of the instrument for the ultrasound biometry, but this is what I'm talking about in terms of contact ultrasound biometry. So the ultrasound probe has a direct contact with the cornea, indenting it, Immersion biometry, it's better because it's immersed in a cup of fluid and it doesn't directly touch onto the central part of the cornea, therefore it's not indenting it. Optical biometer, so this is the IOL master and this is the LenStar equipment. So as I mentioned, these instruments are much better because they allow the patient to fixate directly into the instrument. So the patient sitting on this side here, fixating into the instrument, and the technician will be just taking the readings by looking at the monitor over here. So the fixation on optical biometers, it's available and therefore it makes it much more accurate. Yeah. So the other thing about optical measurements is the axial length measured is expected to be a little bit longer than ultrasonic axial length because it measures a little bit deeper into the retinal pigment epithelium. However, most optical biometers have this measurement calibrated to ultrasonic axial length that is very close to immersion ultrasound, right? So when it comes to immersion ultrasound and optical biometry, the lens constants that we are recommending are no different, so they are the same. So only if the surgeon is using a contact applanation method, then we will be recommending a different set of lens constant values for the calculations. This is a sample measurement of ultrasound measurements. So you can see here what it does measure is, if you ever get a chance to see scans like this, right, on the instrument, it may appear on optical as well. So optical scans do have this kind of representation of the measurements at different parts of the eye. So in this case, it's clearly seen that this is a immersion method, right? Because you see that there is a gap between the probe, ultrasound probe, and the cornea and the anterior cornea. And here you see the anterior cornea followed by the posterior cornea. And then you see the first spike here, which is the reflection of the anterior surface of the crystalline lens. And then next is of the posterior surface of the crystalline lens. And then the last spike here is where it meets the macula or the back of the eye. And you see some other spikes here, which is basically the disturbance you get as the ultrasound goes through the eyeball and then reflects off the other tissues that are in the orbital socket, such as the fatty tissues and the muscles, right? Anything that's behind the scleral wall. All right, so the scleral wall, you probably see it here. And these are all the orbital tissues that follow. Right, so yeah, and one important thing about measuring biometry is also to take note that biometers have got different different modes of operation. So you should be able to set in a different kind of module, right? So for example, if it's a very dense cataract, there are certain ultrasound biometers that allow you to define how dense the cataract is. So that will help to modify the speed of the ultrasound wave traveling through that section. So here the lens section. If it's a very dense cataract, you can tell the equipment that this is a very dense cataract and you need to alter the speed of the ultrasound wave going through that section. Likewise, there are some biometers, most biometers will also have a option to turn on silicon oil mode. So there are some patients that have gone through posterior segment surgery and the vitreous has been completely removed from the posterior segment. So in that case, again, if you indicate that silicon oil mode, where the silicon oil is present in the posterior side of the eye, then the machine, the instrument can make the appropriate adjustments to the speed of ultrasound or the infrared laser beam going through it, and then by doing so, able to give you a much more accurate measurement. So just be aware that these different instruments have the ability to calibrate the speed of the light or ultrasound wave traveling through the different sections of the eye. So the other thing that I wanted to highlight is that recently there has been a new IOL master in the market. So the most recent IOL master is the IOL Master 700. So that is very new in the market, and the previous version is the IOL Master 500. So the 500 still uses infrared laser beam, but the IOL Master 700 uses a swept source OCT. So that's a different kind of instrument altogether, and it's quite new in the market, and it has shown a lot of promise in terms of accuracy in the measurements of the ocular tissue distances. So I'm not sure if you have seen it before, but I intend to give you some idea about how it looks like. So this is how you are still able to see my screen. Yeah, this is how the equipment looks like. It's quite different from the older generation biometer. There's a picture that cites. Yeah, this is the 500. So basically, the 500 is like a standalone instrument. The 700 it's got two pieces of instrument. So the measuring instrument itself, and then there's the diagnostic and the monitor at the side, I suppose, right? So so definitely different because it uses OCT imaging instead of coherence interferometry. Right. So the other thing that is different about the IOL Master 700 is that it has this feature that's called total keratometry. Right. So what it's mentioned in there is that total keratometry measures not just the anterior side of the cornea, but also the posterior surface of the cornea. So what it claims to be able to do is to know what is the true refractive power of the cornea. So very useful, especially in terms of if you're looking to correct the cornea astigmatism using a toric IOL, and if you prefer not to use a normogram but measure the total cornea power, this IOL Master is an option to provide that total cornea power measurement. Whereas, I mean, there are other instruments in the market that does that as well, such as the Pentacam and the Galilei. So those are instruments that are, in a way, providing similar measurements, but the Pentacam and the Galilei are not OCT equipment. So the mode of measurement is different. They're using technology that's called shine fluke imaging, which is taking photographic measurements of the anterior segment of the eye rather than using OCT imaging. So I just wanted to give you some idea about what's new in biometry in the market. Okay, so what the IOL Master provides. So this is based on the IOL Master 500. The 700 does have the similar measurements. So it measures all of this, right? Okay, but the IOL Master has one additional measurement that the 500 does not, which is the lens thickness, right? So the crystalline lens thickness is something that the new model Zeiss IOL Master provides, and that's used for several new formulas which I'm going to talk about later on. So I'm seeing a question here.
Hi, Melvin. Yeah, sorry, this is Hannah. So you see the question there?
Yeah, I just turned and saw it.
Okay.
Yeah, so if a surgeon uses total K, is our official advice when using our technique historic calculator to ensure that PCA box is unchecked. Yes, if the total corneal power is being measured and they have the total. I mean the corneal power is inclusive of the posterior side, then you should uncheck the PCA box. That's the same thing that we are doing with Pentacam and Galilei if they are using the total corneal power measured, right? But be sure to check with your surgeon if they are taking the total K measurements, because they do give both in the IOL Master. Yeah, so existing in the IOL Master, you have these formulas available. In the newer IOL Master 700, you have additional of the newer formulas, like the Barrett formula, and the formulas do have a different set of formulas for total K measurements. So if the total K was measured, there is a different version of these formulas to be used with the total K measurements being done, right? So that is just to take into account that different kind of corneal power is being provided, and it's being is being accommodated for by the formula itself, right? Okay, this is how the IOL Master printout would look like. So you see the biometry measurements, the keratometry measurements, they are there. And even the ACD measurement, so the anterior chamber depth measurement is provided. So do you aware that this anterior chamber depth is actually a measurement of the patient's anterior chamber depth, and it's not the same as the predicted ACD constant that we are providing as manufacturer for our lenses. So these should not be mistaken. They are different. They are very different. They are not mean the same thing. So there are some validation criteria, right? So in case you wanted to check that the measurements are done correctly, there are some general validation criteria. Although there are some that are more detailed that you can find in Dr. Warren Hill's website. There is this validation criteria that he lists out. It's a very long list, But these are some of the general validation criteria that you can look for, right? So measurement to measurement inconsistency, right? So inconsistency in the sense of if the K1 and K2 power difference are more than, like axial length difference measurement, right, between the right eye, left eye is, so these are actually more on left eye and right eye measurement differences. Okay, so it is more to look at your comparison between the left and right eye. Okay, and of course here it's, if you get a very steep or very flat K reading, it's an indication of a different kind of cornea you're dealing with. Less than 40 diopters K readings represents a patient that has undergone post-refractive laser surgery, and that requires a different type of calculation, a different type of formula to be used. If you see that K readings are more than 48, it's a sign that it could be some form of irregular astigmatism, such as keratoconus, differing average keratometry readings between the eyes. So between left eye and right eye, the difference in terms of average K reading, it's more than 1.5 diopters. Then you need to take probably do a remeasurement for both eyes. In K1, K2 with a power difference of more than 3, that means that the astigmatism is really very high. That's also an indication of irregular astigmatism, something that you may want to do a remeasurement again. Astigmatism for either eye, it's more than 4. So this means that, again, irregular astigmatism that you want to check. Difficulty in obtaining measurements, so some instruments may not be able to take the readings for some reasons. It could be because of dry eyes, it could be because of a irregular cornea surface, which is irregular astigmatism. So that's another watch out point. Axial length difference between left and right eye is more than 0.3. Alright, so generally there is always a rule that the left eye and right eye difference shouldn't be too far apart, right? Unless you know for sure that there is a difference in already in the spectacle power of the left eye and right eye, but otherwise the left and right eye axial length difference should not be more than 0.3 millimeters. So if you're looking at the readings, like for example this patient chart, and you're looking at the left eye, the right eye and the left eye, and you're looking at the axial length readings, if they are more than 0.3 millimeters apart, you may want to do a remeasurement. In this case, it's quite close, so a remeasurement is not needed. If you look at the IOL master readings here, between the right eye and the left eye, again, the difference is not more than 0.3 millimeters, so you wouldn't need to do a remeasurement. You can probably take this measurement as alright to proceed. The other thing that you may want to look out for is within the same eye measurement. So it was not mentioned, but one of the general criteria is also to look at within the same eye. You wouldn't want a difference of more than 0.2 millimeters, right? So in this case, you can see that with the immersion biometry, it's actually very accurate, right? So within the same eye, taking these measurements, that standard deviation, it's not more than 0.02, yeah, 0.02, right? So the smallest is, the lowest is 23.14, highest 23.16, so the difference is 0.02. So, the lowest is 0.13, highest is 0.16. So the difference is 0.03. So it's not more than the deviation of 0.2 millimeters. So this should be accurate in terms of a single eye measurement. You can tell that this measurement was done all right. The same for the IOL master. If you look at the IOL master axial length measurements, and you compare that, so you can see that the deviation is not more than 0.2 millimeters here, right, for the right eye and the left eye. Okay, so the Lenstar LS900 is a different brand equipment. It's built by a different manufacturer, right? By Huckstripe, right? And it does also do quite a lot of measurements, but it does lens thickness measurement as well, as opposed to the IOL Master 500 model. So the IOL Master 700 does have lens thickness, right, to go with it. Okay, so again, different biometers have different formulas that are included in the software. So for the Zeiss IOL Master, it's known to have the Olsen formula and also the RPF as well, I believe, and the Holiday 2. For the Zeiss IOL Master, they have the Barrett formula that is included in the software, right? But not the Olsen, right? So there are different biometers do have different formulas that are included in the software. So you may encounter that some of your surgeons are going to be using different formulas because of the equipment that they are using. Right, but however, some of these formulas can be found online, right? So you can actually perform the calculations online through a website, right? Although that has some challenges some risks in terms of of manually entering those readings, because some mistakes can be maybe done in that process when you transfer the data from your biometry manually onto the website. As you're typing it in, there could be some manual errors there. So whenever that's done, it has to be done with a lot of caution. So let's take a look at the formulas then, right? So what are the formulas that are being used for calculation, right? So the selection of the IOL calculation formula really depends on the experience of the surgeon with the formula, right? So some surgeons have got a good level of experience with a certain formula. So one of the common formulas, and it's still very popular, is SRKT, and a lot of surgeons are still utilizing it. But the other thing to consider is the use of formula with different axial lengths. So this is particularly important for third generation formulas that includes SRKT, because SRKT traditionally works well for long eyes and to a certain extent with average size eyes. But with very short eyeballs, SRKT do not perform very well. So that is where some surgeons, with their experience with the formula, they may have a fudge factor when it comes to like short axial lengths. They're using SRKT, for example. They may adjust the IOL power in accordance to the axial length, so that the accuracy is going to be better. Fourth generation formulas are much easier to work with because they do work with all axial lengths. It doesn't matter whether it's a short eye, long eye, or average eye. These formulas work very well. It means the surgeon doesn't need to do an additional fudge factor, so they do not need to adjust their results to get to the IOL power that they need. So fourth generation formulas are much more known to be much more accurate nowadays. I think I have a view of the formulas here. So older generation formulas like Holiday 1, Hopper Q, SRKT, these are considered to be third generation formulas. Now, fourth generation formulas actually start from Haigis onwards, right? So you can consider Haigis an older form of fourth generation formula, right? But the newer fourth generation formulas are Holiday 2, Olsen, and Barrett, and also not listed here, but it's also used by some surgeons nowadays. Is the RBF formula by Dr. Warren Hill. So those are some of the fourth generation formulas that are getting more and more popular. But I would say that Barrett formula it seems right now to be the most commonly used as opposed to the others, just based on the feedback that I'm hearing. So how are these formulas different? If you think about the third generation formulas, those formulas are using just two variables for prediction of the lens power. So these formulas now from third generation, fourth generation, they are known as theoretical formulas. So theoretical formulas are now what is being used. Just a little bit of history on formulas. The very old generation formulas, they are not listed here. So for example, SRK and SRK2, those formulas are based on regression, right? So those are regression formulas. What we mean by regression formulas is that they are purely based on the axial length of the patient's eye to predict the IOL power. So it is less accurate than these theoretical formulas, because the new theoretical formulas, they use the formulas to using axial length, cornea power, and different measurements of the patient's eye, such as the anterior chamber depth, the lens thickness, and the white-to-white measurements. All this go in to estimate where is the effective lens position of the IOL. So when we say the effective lens position, means where is the IOL positioned in the eye after implantation. So these formulas have different ways to provide an estimation of that lens position after implantation, right? And they have different results as an outcome of the way they are performing the estimation, and they also have different results also because of the different measurements of the patient's eye they are taking to calculate or estimate the effective lens position. So just give you an idea of what a typical formula would look like. So this is taken from a really old formula, the SRK formula. So you can see the relationship between the lens constant in here. The SRK formula uses A constants. The A constant is subtracted from 2.5 times of the axial length and subtracted from 0.9 of the average keratometry reading, right? And that gives you the power of the eye. So as you can see here, it doesn't actually predict where the lens position would be, but it's just directly does that calculation based on axial length, average K readings, and the lens constant. But this relationship still still has a similar effect with the other formulas that you see here. So this is where you can understand why we say that axial length reading are very critical, right? So axial length reading, if it's any error that's performed in the axial length reading, then the error will be amplified 2.5 times. So if there was, example, an 1 millimeter error in axial length reading measurements, then the power that's resulting will be 2.5 times, 2.5 diopters of error. Whereas K readings would be closer to the same amount of error that they were having, because it's multiplied by 0.9 times. So any keratometry reading error would be similar in terms of the IOL power error that it is inducing. But axial length error is inducing 2.5 times of its error, right? But it varies, so it's just a guideline, 2.5 times and up to 3 diopters, because it depends on the eyeball length. So the longer, the shorter the eyeball, the higher is the magnitude of the error. So if you have a very short eyeball, then the error of measurement would contribute to even 3 diopters of the IOL power error. So when you look at a formula like this, you can tell that there is a requirement in formulas to input the lens constant value as well as the patient measurements that are included here. So patient measurements in the SRK formula include axial length and average K readings. The constant that's required in SRK formula is the A constant value, right? So now different formulas require different length constants and different measurements to go with it, right? So let me just show you a summary of what are the measurements and constants that are required. So if you take a look at the measurements that are required for each of the different formulas, so if you see the third generation formulas, so SRKT, Holiday 1, Hoffer Q, they just require axial length and keratometry readings. When it comes to Haigis or fourth generation formulas, that's where it becomes a little bit more accurate, and likelihood is because they are using more measurements from the patient, right? So Haigis includes anterior chamber depth measurement. The Barrett includes not just axial length keratometry and ACD, but also lens thickness. So meaning the thickness of the crystalline lens, and white to white measurement, which means the limbal to limbal measurement. Some people call it the cornea diameter. Olsen formula uses, in addition to the axial length keratometry and ACD, lens thickness, it also uses preoperative refraction. Now this preoperative refraction is the refraction that the patient has prior to having cataract. So as we know, if you're having cataract, then the refraction would be altered slightly. So from what we understand about this formula, it works best when the refraction is performed, when you can obtain the refraction results prior to the cataract developing in that patient. Holiday 2 has everything that you see up here, but inclusive of one more factor, which is age of the patient, right? So we can tell that for the fourth generation formulas, why they are doing well, because they have a lot more measurements from the patient's eye. So the prediction of effective lens position is going to be much more precise as compared to the third generation formula. Did someone have something to ask? Someone on unmute? Okay. All right, in terms of lens constants, so what lens constants to use for the formulas, right? So if you are using SRK formulas, so SRK2 and SRKT and Barrett, they all can be used with the A constant value. All right, so SRK2 actually has a different lens constant value, A constant value. So please check it out on the ULIP website. The lens constant value that's indicated on our packaging is for SRKT. Right, and Barrett Universal 2, it's using it's actually using a lens factor, right? But this is converted easily from A constant values. The conversion is done automatically in the Barrett website, all right, or even in the IR Master. If you're using it, it automatically converts the A constant value to a lens factor. So let me show you what the lens factor looks like. So this is the Barrett formula, which you can find it from the website. All right. You can choose the lens here, and it automatically provides the lens constant value and the lens factor straight away. So there is a conversion that is done automatically. So you don't really need to provide this. It is automatically populated in the IOL master as well. Now there's a slight difference in the lens factor value that you see here versus that in the IOL master, but that's not significantly different to cause a difference in the IOL power calculation. So not to worry too much about that slight difference. Okay. So the other formula that is not listed here is RBF. So RBF uses predicted ACD. So I didn't list it here, but I can show you the formula. So the formula can be found in some of the instruments like the lens star, but you can also do it online, right? So you either look for it, right, under the Dr. Warren Hill website, right? So this is a website, dr-hill.com, where you can obtain the Warren Hill formula, the RBF formula, or you can actually obtain it from the I think it's ASCRS website, yeah. So from the ASCRS website, it does have a link to the RBF formula as well, right? Either ways, it's the same one. Yeah. Yeah, it's version 2, so it's the same formula. Okay. All right, so I'm mistaken actually. You need to provide the A constant value, so not the predicted ACD. All right, so you can probably add to this list here. Probably add to this list here that the RBF formula also uses an A constant value. Okay, so what does the RBF use in terms of the variable? So I didn't list it here as well, but it uses some measurements from the patient's eye as well. So this includes axial length, K readings, CCT, meaning central cornea thickness. So it's the only formula that's now available that's using central cornea thickness. And anterior chamber depth, right? Lens thickness in white to white. So there's quite a few different variables that it's using. Although I think this one it's not compulsory, it's not mandatory to enter. There are some mandatory measurements that you need to enter, but this is something that you may not need to enter if you do not have the value. Right. So similar also for the Barrett formula. You can see that there's some optional variables that you can put in, right? But if you do not have these values, the formula will still perform the calculation using just the axial length, the K readings, and the anterior chamber depth. Refraction here is not the preoperative refraction. This is the refraction value that you want the calculation to display. That means if you want a formula to show what is the IOL power to get to emetropia. So you put it as 0. All right, because some surgeons may want to do like maybe a mini monovision or a monovision result, so they may input a different value there so that the calculation shows what is the power that's getting you to a -1 result, for example. But generally the case is emetropia, which is 0. Okay, so choosing the right formula, right? It's important, right? Because the patient's expectations is independence from spectacles, right? And also elimination of astigmatism is high on their expectations, right? And so post-op refraction, we do expect it to be within 0.25 diopters, whether it's plus or minus. You wouldn't want to go beyond 0.25 diopters because that's going to create some loss in visual acuity. Right, so essentials, other things to look out for is to make sure that you have consistent measurements for keratometry and axial length. Correct IOL constants are being used and appropriate IOL formulas are being used. Right, so appropriate formulas, if you're not using these new generation formulas, you probably want to start doing it and cross-reference it to the older generation formulas. So for example, if the surgeon is using a older generation formula and the eyeball is pretty unusual, it's quite long or it's very short, then you may want to suggest to do a cross-reference by measuring, by doing a calculation on a newer generation formula and cross-check the result to that of the older generation formula. Correct IOL constants is being used, so this goes back to the different biometry that's being used. So if they are using applanation method with ultrasound, you would want to use the ultrasound constant that's provided. So for our Technis ZCB, that is recommended as 118.8. If they're using optical or immersion methods of biometry, then you would want to use 119.3 for our Technis one-piece IOL. Right, so in case it's a very short eye and there is only third generation formulas available in that ultrasound scan, the Q may offer a better accuracy as opposed to the other formulas. So the other formulas are, the other third generation formulas such as Q, Holiday 1 and SRKT are doing quite alright in terms of the average axial length. SRKT does very well for the very long eyes, but Q does very well for the extremely short eyes. But if you're using, like again I said, if you're using the new generation formulas, then you wouldn't need to be concerned of whether it's a very short eye or a very long eye. Right, so like I said, choose the correct constant according to the axial length measurement method that's being used. Alright, so the other thing I want to touch on is IOL constant personalization. So IOL constant personalization comes about because if you think about formulas, right? When we are performing calculation, there are many different patients with different eyes, different eyeball lengths, different sizes of the axial length, anterior chamber depth, lens thickness, cornea diameter. So every eye is going to be different, right? And the other thing that you're going to be faced with is different surgeons, right? So different surgeons, they may have performed surgery in a very different way, right? In terms of the way they perform the capsulorhexis, the size of the capsulorhexis, the incisions that they construct. That's also going to be quite different from surgeon to surgeon. The different instruments that you use, right? So if you look at the IOL master versus the lens star, they are different instruments. So the axial length that they measure, it's going to be quite different. Even looking at the same instrument, if you have two instruments that are the same, like an IOL master, two IOL masters, and you use the two IOL masters to measure the same patient eye, there could be some variation in the readings. Keratometers as well. Different brand keratometers may give you a different keratometry result, right? And then if you look at surgical techniques like non-laser or laser surgery, right, or manual surgery. Laser means using the femto laser cataract equipment, right, to perform capsulorhexis, incisions, and lens fragmentation, as opposed to manual surgery, which is the traditional phacoemulsification surgery, right, and also the different techniques that the surgeons are using to disassemble the nucleus. So there are many different variations here, right, that we need to take into consideration, right, when performing calculation. When you look at patients' eyes and different patients, that difference is accounted for by the variables that you're measuring in each patient. So if we go back to these variables here, these variables that we are taking, we are measuring for each patient. Yeah, these variables here that we are measuring, right, for each patient, right, they are going to be they will help to account for the differences from each eye, each patient, each eye, right? But how do we then account for the differences between the surgeons, the instruments, and the surgical techniques? So the only way that is done to account for these differences is what we call lens constant personalization. So this is where personalization of the lens constant comes in, right, to be able to account for the differences in instruments, surgical techniques, and different surgeons, right? So different surgeons, different instruments, and surgical techniques can result in a slightly different lens constant, right? And that needs to be personalized. That needs to be personalized, right? And by doing that, we can get better, much better accuracy, because by using a personalized constant, it can account for the variations in terms of the different instruments or the techniques the surgeons are having. Right. So when we talk about personalization, we talk about being able to get the refractive result on target. Right. So getting it on target. Right. So if your results are all over the place, if the outcomes are all over the place, meaning you have a mix of hyperopia outcomes or myopic outcomes, then it is not a problem with personalization. That is probably a problem with instruments, accuracy in measurements using instruments, or a incorrect use of formulas. But if you notice that all the results, the outcomes of the cases are closely similar, are very similar in their outcomes. So for example, if you had 20 patients and maybe 18 of them, or close to 20, even 20 of them, all of them are hyperopic in outcome, then you have a very consistent result that is not optimum. Now, then that gives us the opportunity to shift the results to the target, right? To shift the results to target. So the key then is to find out how far away are these results from the target, and then what they would do is to titrate the lens constant so that we can achieve emmetropia for the future cases of the surgeon. Right. So the process, right, it's as what I said, performing the surgery, take the post-op measurements, right, and then collect 20, 30 successful outcomes, right, and then calculate what's the surgeon factor. Right, so I wouldn't say it's successful. It would be not so successful because it's not accurate in terms of the result. That's why you need to perform personalization. Based on that, those results, you can then calculate what is the surgeon factor. Okay. So in terms of personalization, we are not performing the personalization, right? This requires a special formula to do it, and there are some third-party websites that provide this service, right, to perform the personalization, right? So for example, if you went into Dr. Hill's website, there is the physician downloads here. Oops. Yeah. So there's the physician downloads here, which you can go to, right? So it's called the Haigis formula optimization, right? So although it optimizes the constants for Haigis, the Haigis constants, which are the A0, A1, and A2 lens constants, right, for Haigis. But this optimization Where was I? This optimization also provides optimization for your A constants and your predicted ACD values, right? So there's quite a bit of data that's required, right? And if you click on this, it brings you to a page where you click on this one, right? And you have some instructions to specific to the data that needs to be collected, right, and submitted to Dr. Hill, right? So this is the spreadsheet that you would need to download and collect the data, right? Okay, and it does provide a constant personalization and predicted ACD personalization as well. Now, another way to do it is to do it on the biometers. So, like the optical biometers, like the IOL Master or even the Lenstar, they have a built-in personalization software that can be used to perform lens constant personalization as well. So that is another option to go to, right, or to discuss or suggest to your surgeon, right? That is another option using the biometers to do it.